We're continuing to look at applications of graphs of the sine and cosine function today. And our first example is the harmonic spring. I know you've seen something like this before. You've got an object on a spring, you pull it down and release it, and it bounces up and down. The motion of the object can be modeled by a sine or a cosine function, so that's what we're going to take a look at in this first example. We know that the object starts at equilibrium. It's not moving up or down before we pull on it. And it takes 4 seconds to complete an oscillation. So it's back to equilibrium at 4 seconds, which means halfway between the two, it is at equilibrium. And because we pulled it down first, halfway between 0 and 2, it is at its minimum. We pulled it down to 20 centimeters. And when you release, it jumps up just as much as you stretched it down. So it goes up to 20 centimeters at its maximum. So this function will look like this curve. And of course, before we can answer where it was exactly at 1.2 seconds, we have to write the model for our graph. A is our amplitude. Because we don't have a vertical shift, we can clearly see our amplitude is 20. The object was pulled down 20 centimeters and bounced back up 20 centimeters. D, as we mentioned, there's no vertical shift. Our principal axis is the x-axis. To find B, remember it is 2 pi divided by the period of the function. In our case, it takes 4 seconds to complete an oscillation and get back to equilibrium, which simplifies our B value to pi over 2. C would be a horizontal shift. In this case, sine is starting at 0. However, the parent function would go up from 0. Ours is going down from 0. We have no horizontal shift, but we do have a reflection. So we're going to go back and modify that A value to negative 20. Putting that all together into our function, we get negative 20 times the sine of B, pi over 2. Because C is 0, we just get to do B times x, and our D is 0, so we don't have anything to add or subtract either. And now we will use that function that we just wrote to answer our question. As a reminder, it was negative 20 times the sine of pi over 2x. Time is the input, so we're going to substitute that 1.2 in for x and solve for the height of the function. When you put this into your calculator, make sure you are in radian mode. We used 2 pi for the period, which is in radians. We did not use 360 degrees. So our input needs to be radians. And I got about negative 19.021 centimeters. Because the value is negative, what it really means is that it was about 19 centimeters below equilibrium at 1.2 seconds. Next example, we're going to be looking at tidal waves again. In this example, we're given the equation for the function of the tides at Boston Harbor. T is the number of hours past noon. Y is the height of the tide. Our units are feet. The question this time is how many hours between noon, time equals 0, and 12 hours later, or midnight, is the tide above 5 feet, or 5 feet or greater? We're going to solve it by graphing the function, and then we'll use the graph to answer the question. Identifying that essential information, A is 2, that's the amplitude of our function. B is pi over 6, which means the period is 2 pi divided by pi over 6, or times the reciprocal. So our period, the pi is canceled, 2 times 6 is 12. D is plus 4, which means that's our principal axis, and we have no horizontal shift. There's no C value. Scaling our y-axis, I'll go by ones. The height of our function is 2, so we'll go 2 up and 2 down from that principal axis. The period is 12. We'll chunk that into 4s. And cosine starts at its maximum, down to 0, minimum, back to 0, back to maximum. In order to answer a question, we need to know where the tide is above 5 feet, 5 feet or greater. We will have to estimate, it depends on how accurately we drew those curves, but that's 5 feet. So it looks to me like we've got about 2 hours here where our tide is 5 feet or greater. Plus over here, we have another 2 hours where it's 5 feet or greater, giving us a total of 4 hours that the tide is 5 feet or above.